Okay, welcome back to part 3 of my tutorial on how to use Cloud Compare to analyze three-dimensional data. So I'm going to take you to some models that I had prepared before. This is a gravel road in rural Story County, and I put some markers down here. You can see them there and there. This is from a laser scan, and this model is from Structure from Motion. You can see the targets there too, so I'm going to show you how you can compare these models to one another. Now you can compare between collection methods, as I have, or you can compare over time, three-dimensional changes over time. The process is the same. Now, the first step is to select both of these. I have already segmented these, I showed you how to do that before. Now I'll show you how to register or align. Now the first thing you would do, these are already aligned, but you would match the scales. So I'll just move these around a little bit just for demonstration. Move this over, maybe rotate a little bit. Okay. So what would usually happen is you would have these would be far different scales. Well, I'll change the scale here too. So the scale of this, you have no idea what it's going to be. It could be 100 times smaller, it could be 50 times smaller. You don't know what you're going to get. Okay, so you have this thing, you upload both of these models, and you have this, and then you're thinking, where did the other one go? You select it, can't find it. You're like, oh look, it's over there, and it's really tiny. So the first step to make these somewhat the same is do registration, match scales. Always do the laser scan as the reference entity so that you have everything in real world coordinates. I'll just do PCA for matching criteria, and it doesn't really matter what you do. So now these are roughly the same size. Next I'm going to select this cloud, click the rotate, translate rotate button. I'm going to get these, I'll just get them side by side for now. So I have, again, get my bearings of which is which, make sure that they're both right side up. You don't want to try to compare one of these. One of them is upside down, so that looks fine. Click OK. Now I will select both models. Registration, align point pairs picking, reference will be the laser scan. Okay, that looks good. So you're going to need at least 3 points. I think I can get 4 points from here, so I'm just going to click the corners of these targets that I have here. Do those corners and these corners. Just select whichever benchmarks appear to be most reliable. So that looks good. Error is, this is a millimeter, so this is 3 millimeters, 5 millimeters. I adjust the scale as well. So these look pretty closely aligned. You can see they're a little off. I'll click OK. Now you have the matrix as well. You can, if you're a math type person, you can use that matrix for, well, whatever math type people use matrices for. That is not me, so we will move on. Now the next step is registration. Find registration iterative closest points. I'm going to swap these. Model should be laser scan. Now adjust scale, final overlap 100%. These are pretty much the same. If they're not very close, you might want to do 90, 80%. You could go lower. The rest of these look good. Now what this is doing is reducing the root mean squared error of the point clouds. and when it gets down to after each iteration, it calculates the difference. Now when the difference gets down to, I believe, 10 to the negative fifth, then it will stop the iterations. Now this is about 24 millimeters, so this should be pretty good. Doesn't take too long. If you're working with a large point cloud, this could take some time. I'd point out, if you are doing this yourself, you should set well-defined benchmarks. Okay, here's that matrix for you math guys out there. Scale was changed slightly. It wasn't moved very much. This is 5,000 points. It sampled down 5,000 points between each cloud. And okay. Now, I've already calculated the distances before, but I'll show you how I do that. It's very simple. You just select both of the clouds, do distances. You can do cloud to cloud distance, and max distance, let's just say 100 millimeters. It's not going to be any more than that. I usually do the quadratic height function for the local modeling. You usually get slightly better results, especially if you are working with a sparse model. And then just do compute. Now this was saved as a scalar field. If you want to access the scalar field, first you need to change color to scalar field, or you can do RGB or none. Now in the cloud, scalar field, cloud to cloud absolute distance. Here is the distance between the two. Now I'm going to do visible scale, so this shows you the distance between the clouds. Now this is pretty close. If you want, you can change this, so you just have a better idea of what the points look like. I'll just keep it out here about 60. From here you can analyze it in a variety of ways. You can do histogram. You want to see what the 95th percentile of points are. In this case it looks like it's 35. You can change the bin values. You can also do a statistical model, Gaussian or Weibull, and this will show you the Gaussian mean and standard deviation of points. You can also analyze using a plugin that was developed by some very smart people in, I believe, Switzerland or France, one of those two places. Oh, Madame Curie. So they do a lot of the same things, but they have a slightly different way of calculating the normals between points. So I'll just show you what that looks like. I have it already up right here. So you can look at the standard deviation of the cloud 1, cloud 2. You can look at significant change. This is based on 95th percent confidence interval. You can look at 14% of the points are outside that interval, so this is a pretty good scan. Distance uncertainty and M3C2 distance, and this is signed, so you'll see these points are actually lower in the one cloud than the other, and this is higher. Again, you can do the same Gaussian, do the histogram, look at points, and it's just that easy.